All right, let's go back to the slideshow. We've practiced the beginning. Remember what the beginning was? State the claim and identify the null and alternative hypotheses. We've done that. So the middle. Calculate the test statistic and its p-value. Compare the p-value to the significance level alpha. That doesn't make a bit of sense right now. We have to talk about what a test statistic is, what a p-value is. We have already talked about significance levels. The test statistic for a sample statistic is the number of standard deviations that it lies from the population parameter. What word pops in your head, or what phrase pops in your head when you see the number of standard deviations from the z-score? We're finding a z-score or a t-score, depending on whether we know the population standard deviation or don't know the population standard deviation. All right, but we're finding out how far something is from the mean, or how far something is from the population proportion, or from the population standard deviation. The test statistic is just how far away from the whatever it is. We will use the calculator to find the test statistics for sample proportions and sample means. You don't have to memorize any formula. There are formulas in the book. I think I decided not even to put them in the slideshow. I'm just going to show you how to get them on the calculator. For example, let's consider the claim that the XSORT method of gender selection increases the likelihood of having a baby girl. Preliminary results from a test of the XSORT method of gender selection involved 14 couples who gave birth to 13 girls and 1 boy. What does your gut say? Does this procedure seem to be working, or nah, not really? Heck, if you got 13 out of 14 girls, something, I mean, that's not likely to happen by chance, so something's going on. Switch to one I can write on. Preliminary results are that 14 couples gave birth to 13 girls and 1 boy. State the null and the alternative hypotheses. Before you can state that, you have to state the claim. What is the claim that the IVF Institute is making? All right, you got to give me something other than a pronoun there. What population parameter are we talking about? A proportion, a mean, or a standard deviation? A proportion. All right, so the claim is that the proportion of girls is greater than 0.5. That is false if what? All right, and the way that you would say not greater than is less than or equal to 0.5. So what is the alternative hypothesis? And notice here I used H1 instead of HA throughout the slideshow. Just get comfortable with both of those. What is the alternative hypothesis? The one that doesn't have an equals in it. P is greater than 0.5. What is the null hypothesis? It's always plain old equals. What is P for this sample? How would you find the proportion of girls in this sample? Yeah, 13 out of 14. That's how you find a proportion. I don't think I have that written down. Somebody give me. All right, give it to me as a decimal, and let's go ahead. Give me 4 decimal places. Okay, did I understand you correctly? Okay. This this sample was almost 93% girls. That's way more than you would expect by chance. The mean, without any kind of procedure, would be 0.5. And in this sample, the mean is way out here at 0.9286. Now, we don't know how to use the calculator to find the z-score yet, but let's play like we did, and we did it on the calculator, and that z-score comes out to be 3.21. That's more than 3 standard deviations from the mean. Is it likely or unlikely to get something more than 3 standard deviations from the mean? Highly unlikely. All right, so a z-score of 3.21 is unusual. Thus, it would be unusual for a sample to have a proportion of 93% of the girls if the treatment was making no difference. I think that's all we needed to say on that problem. Let me go to the next slide. Yeah, that was all we needed to say. Just this is the concept of a test statistic. The test statistic tells how far away from either the mean, the population proportion, or the population standard deviation a given sample statistic is. Yes, or it could be P for population proportion. All right. The critical region or rejection region is the set of all values of the test statistic that would cause us to reject the null hypothesis. The critical region can be in the left tail, the right tail, or both tails of a distribution. We're going to have to think hard about that. I don't want to switch back to Elmo right here, but if you drew the little picture that I did beside the last slide with proportion equals 0.5 in the middle and proportion equals 0.92 way out in the right end, we would, let me think before I say that. We would say something is unusual if its proportion is more than how far from the standard deviation, not standard deviation, but from the population proportion. If it's more than 2 standard deviations, so 2 standard deviations in that case would be our critical value. The critical value, the critical region is just shade everywhere such that if your test statistic falls in this region, Miss Regina, your face is hilarious. Let me do Miss Regina for you. I think I might be dying, or I think I might be already dead and gone the wrong way. Hang in there. It gets better. No, it's not going to get worse. Some things take a long time for me to make your light bulb come on, which is basically my job. I'm a light bulb engineer. It takes a long time for us to even establish a foundation on which you can build a framework that makes your light bulb come on. Sometimes you just have to hang with me a few minutes. And then by the time you get to the end, you go, oh, is that all? Why didn't you just say that to begin with? Well, I couldn't say that to begin with because you didn't know any of the words to begin with. We're getting the words now. The critical region or rejection region is the set of all values of the test statistic that would cause us to reject the null hypothesis. It could either be the left tail, the right tail, or both tails. We need pictures. That first picture, let me see if there's anything else. Yeah, the first picture is the picture that you would draw for what is called a left tail test. A left tail test is when the rejection region is in the left tail. If you get a test statistic that's anywhere out there in the blue region, you're going to reject the null hypothesis. The middle picture is that of a right tail test. The rejection region is in the right tail. If your test statistic lies anywhere in that blue area, you're going to reject the null hypothesis. And then the third picture is called a two-tail test, when you're going to reject the null hypothesis if your test statistic is less than something or greater than something. And then the word we have seen before, the significance level alpha, is the probability that the test statistic will fall in the critical region when the null hypothesis is actually true. I tried my best to leave that sentence out, but then you can't do the homework. So we've got to think hard about critical significance level. Just like with confidence intervals, I said, I want a 95% confidence interval. You immediately knew alpha was what? 0.05. All right. Or I want a 90% confidence level. That means you know alpha is 0.10. Same thing here. It's the probability that even if the null hypothesis is true, we would still get a test statistic in the rejection region. Basically, it's the chance of a false positive. The null is going to be true, but we're still going to reject it. What's the probability of that happening? It all goes back to how confident we want to be in whatever statement we make or whatever conclusion we draw. All right, biggie of the day is p-value. We have a little p for, now what is our symbol for sample proportion? Sample proportion, not sample mean, sample proportion. With a hat on it. P-hat. Remember, p-hat is the sample proportion. P no hat is the population proportion. Now we have a capital P, the p-value. That has nothing to do with the other two. Oh, I didn't make this up. The p-value is the probability of getting a value of the test statistic that is at least as extreme as the ones representing the sample data if the null hypothesis is true. What the heck? Let's think about it. For a left tail test, that means the critical region's in the left tail. Let's say I find out the test statistic, maybe that z-score we had for the XSORT method a minute ago, z is 0.32. Wait, that's positive, so it'd be to the right. For some other example, we may have a test statistic being negative 0.3. If we decide to reject the null hypothesis, if the test statistic is anything less than negative 0.3, then the p-value is the probability that something's going to be less than negative 0.3. For a right tail test, we're going to reject the null hypothesis if our p-value, if our test statistic, now I don't know how I started that sentence. Let me back up. Reject, I said we're going to reject. Okay, I couldn't remember if I said reject or fail to reject. We're going to reject the null hypothesis if our test statistic, no, I'm not saying that correctly. Yes. Yeah. No, P is the probability, the likelihood of getting a test statistic way out here. That's what p-value is. The probability of that occurring, whatever, the probability of that occurring if the null hypothesis is true. That's what a p-value is. There is a reason that you have to know whether you're dealing with a one-tail test or a two-tail test, because when we tomorrow use the button on the calculator that will calculate the p-value for us, one of the things that we have to put in is whether it's a left tail, a right tail, or a two-tail test. We have to tell the calculator that in order for it to give us the right p-value. All right. If the alternative hypothesis is less, let's say p is less than something, or mu is less than something, or sigma is less than something, if your alternative hypothesis has a less than in it, you're going to have a left tail test. You're going to reject the null hypothesis if your test statistic falls out there in the right or left tail end of the normal distribution. So if the null hypothesis, if you want to assign some words to this slide's kind of short on words, but what you could add is if the alternative hypothesis has a less than, this is a left tail test. That means the rejection region is in the left tail, and we're not going to call it the acceptance region, but the fail to reject region is everywhere else. If your alternative hypothesis has a greater than in it, then it's a right tail test. That would mean that your rejection region is in the right tail, and unless your test statistic lies out there in the right tail, you're going to fail to reject the null hypothesis. If the null hypothesis says something is not equal to, that means less than or greater than, that's when you know you have a two-tail test, and we will reject the null hypothesis if our test statistic is way out there in the left end or way out there in the right end. You remember that problem on the practice test? And if I remember correctly, we didn't have one just like it on the real thing. But on the practice test, we were supposed to find the probability that Z was over here or over here. How did we do that? Find the area in the middle and subtract it from 1. You've already found the p-value. You just didn't know it. P-value is that probability that your test statistic will lie in the red region. All right, go back to XSort. The likelihood of having a baby girl, let's see, the claim. This is a different claim. Consider again the claim that with the XSort method of gender selection, the likelihood of having a baby girl is different from 0.05. Doesn't say less than or greater than. It just says different from. There. Then what is the claim? That's what different from means, anything but. So the claim is that P is not equal to 0.5, and we will reject that if what? If P equals 0.5. Always write your alternative hypothesis first. Which one of those, or what is your alternative hypothesis? Does not equal to, and the null hypothesis, P does equal 0.5. The claim that the likelihood of having a baby girl is different than 0.5 can be expressed, as we did on the previous slide, as P is not equal to 0.5, so the critical region is in both ends. It's a two-tailed test. We will reject the null hypothesis if the sample proportion is significantly either less than 0.5 or greater than 0.5. Our p-value would be the area in both tail ends. So earlier we were given z equals 0.321. Let's see. We use the TI 8384 to find that the area to the right of 0.321 is 0.0007. How do we use a calculator to find that probability in the right tail is 0.0007? We're not looking for a z-score, we're looking for a probability. That's normal CDF. I could have typed that for you, I didn't think to. When I say we use the calculator, we use normal CDF 3.21 to 9999. Oh, I know why I didn't type that. Because we don't know the mean and the standard deviation. All right, I didn't say that this was a normal, standard normal distribution, so we can't assume that it is. But if you had given me the mean and the standard deviation, then I would have used normal CDF 3.21 to 9999, comma, mean and standard deviation, and it would have given me this value. That 0.0007 is this area. I don't want to write on the screen here, but draw you a arrow, and this end is 0.0007. So that's the probability that z is greater than 3.21. What's the probability that z is less than negative 3.21? Same thing. So what is the probability that your test statistic will be in either of those regions? This plus itself, or this doubled. The p-value is twice the area to the right. So 2 times 0.0007 is 0.0014. That's the p-value for this hypothesis test. Such a small p-value shows that there's a very small chance, a less than a 1% chance of getting the same results that were obtained in the sample if the XORT method had no effect. If the probability is actually 0.5 for having a girl, then the probability of getting that is less than 0.0014. That suggests that when using the XORT method, the likelihood of having a baby girl is different than 0.5. Remember, it was 93% girls? 93% girls is way more than 50% girls.